Good morning, good afternoon, hello. Good afternoon, good afternoon. All right, I'm gonna do this. Hold it. I've been slow with my board lately. We're bored with my slow. We are coming. Okay. Good afternoon. Yes. Okay. I'm gonna say yes. Okay. What did I just? Okay. So who just said what? Yes, God afternoon. Yes, that's my favorite kind of afternoon. Good afternoon. No, I'm not correct. Anybody's good afternoon, Katie. Good afternoon, Alexis. Good afternoon, Emily. Good afternoon, Claudia. Good afternoon, Stephanie. Good afternoon, Brandon. Good afternoon, Paulina. Good afternoon, Jenna. And it seems, oh, am I? Oh, this is interesting. Okay. Yes, it is definitely that time of the year or the semester because I am the only one in the video room. And, oh, okay, wait. And yes, I can understand. And there's Jada. Good afternoon. Okay. Okay. Give me for a sec. All right. So we're going to, and good afternoon, Maria. Oh, it starts tomorrow. Oh, yes. Oh, thank you very much. God, I keep thinking it's starting Friday night. Right. It's starting tomorrow night. Yes. Thank you very much. Yes. I appreciate it. I don't even know if I'm allowed to acknowledge that publicly. So tricky, but yes, thank you. Regarding the person in direct chat who's saying about tomorrow night. And thank you for reminding me that I'm totally off in my sense of time. Okay. Yes. Okay. Okay. I want to get straight to the okay. Yeah, I know it is definitely that time of year, isn't it? It's the most okay. Um, all right. I'm going to just keep going with where we were in the homework yesterday. I think that's the best thing. So bear with me for one more second. Just pulling it up. Okay. Yeah, I'm just gonna. Okay. So we're in the okay. Oh, and someone else is here. Bear with me. I think it's homework 9. Someone just came in. I'm on 2 screens at once. Sorry. Okay. Okay. Right. Okay. Oh yeah. All right. So, sorry for the delay. I think there's homework 9. I don't remember if it's called. Well, yes. We're in the middle of the boulder going down the inclined plane problem. I'm just gonna keep. I know we're. Yes, it's homework 9. Okay. All right. I'm just gonna keep going with it. Or part. So 1D. D wants to know what is the net work done on the boulder, right? So that means, in effect, what's the work done by the net force on the boulder as the boulder rolls down the ramp. Okay, this boulder is rolling down the ramp. Oh, and at this point, we know there's friction on the ramp. So it wants to know the net work done on the ramp, on the boulder as it rolls down the ramp. So you could think of that one of two ways. You could think of that as the work done by the net force along the ramp, or you could think of it as the work done by one force plus the work done by the other force, and the two forces are going in the opposite direction, it comes to the same thing. So I'm going to do it this way. I'm going to say the network is the sum of all of the works. The sum, right? Net always means sum, but some of the works in this case, one of the works in this case is negative. So it'll get a minus sign, but we really are adding up all the works, and the work and that means the work done by gravity on the way down, minus the work done by friction, right? And the work done by gravity, and we figured out these numbers already earlier, but the work done by gravity on the way down is mgh, and the work done by friction, we were already told, is 70 times 11 over sine of 33. We already got these numbers 2 days ago, but I don't have them with me. So we have 9. I think you're going to have to, someone may have to correct my numbers in a second, because I know we got these numbers yesterday and I'm not looking at that sheet right now. But yeah, okay, no, I think I agree with myself. Yeah, okay, so I'm saying that the network done, I'm saying that the network done, I'm saying the network done on the boulder as it travels down the ramp is approximately, and I'm on 3 different screens here at the same time, so I'm going to look at the chat in a second, but I'm saying it's approximately 7,936 joules, or 7.94 times 10 to the third joules. Let me just look in the chat. Okay, it seems like it's okay with you guys. Just 2 quick, I'm just going to keep going, so we can finish this sheet before the end of the semester, but just a couple of notes. The work done by gravity was just mgh, right? That was our big conclusion from yesterday. Like, the work done by gravity is always mgh. And also note the work done by gravity, while this thing is rolling down, the work done by gravity, no matter what coordinate system you pick, the work done by gravity is positive because the displacement is proceeding in the same direction as the force, right? They're both down. Whereas the work done by friction is definitely negative because friction is pointing up the plane while the displacement is down the plane. And just notice, too, I'm going to keep going, but just notice, it's not so much that you want to memorize that work done by gravity is always mgh and work done by friction is always fx or something like that. I mean, you can, but just, it's not arbitrary, right? You see the logic. Both the mgh and the f times x is the result of our multiplying a component of force, which is just parallel to displacement, with the displacement itself, right? Like all right, I'm just going to say this one. In the case of mgh, you're doing force times displacement. And in the case of friction, you're doing force times displacement, right? Like you're always picking displacement and force components that are matching each other. In the case of gravity, it's the force times the component of displacement that's parallel to the force, right? It's like the force is down, so you just pick the downward aspect of displacement. In the case of friction, the displacement is along this way, and the friction is along this way. So you multiply them together, they both match. Okay, I'm over talking this. That's the answer to D. I'm going to go on. Bear with me. I'm also going to change the view on the screen. Sorry. Obviously, stop me at any. I know we're all. It's whatever. It's the week that it is. Oh, and I'm going to keep going. But I'm one question I would like to know in the chat from you. If anybody's like paying attention, let me know in the chat at your. Please confirm for me, please. You have lab. You're the section in your section. You have lab with the Walterses on Fridays. Is that confirmed for me in the chat, please? Like that you have lab this Friday in person with the Walters, I believe. Is that actually, I'm going to look right now. Is it? Yeah. Oh, wow. That was an amazing response from everybody. Oh my God. Thank you. Okay. Especially given a day that I'm like off base and no one's in the video. It really, oh, and there is stuff in the chat. I'm sorry. Wait a minute. Okay. So first of all, thank you. That's like a lot of you just responded. So you are totally there. Thank you. So it's Friday. Okay. So I'm also going to tell you that I'm just trying to get through this last homework so we have clarity, but details about exams and all of that. Well, bottom line, I can assure you that in Friday, in the lab with the Walters, you'll be working on a practice exam that you will get that in time for that. And it's a practice exam for the final. Okay, so those of you who are, and of course there's, I'm sure that, and I will be more detailed about grades and all that stuff, like either at the end of this class or on Monday, but well, I'll just say this quickly now. You'll get a practice exam that you'll work on in Friday with the Walterses. It'll be post, and it'll be take home and all that. It'll be a lot shorter than your midterm. Okay, I'm going to say this quickly now because I'm on the, your final will be shorter than your midterm. It'll be take home just like your midterm. It will be, it'll be posted like probably Monday night after we have our last class next Monday, right? And it will, and then finals start. I get all my dates confused, but all this will be posted for you for Friday, but it'll be due back like, wait, finals end. It'll basically be due like right before. Sorry, it'll be posted the night after your last class, and you'll have like 4 or 5 nights to do it. And you'll turn it in by Google Classroom before the final week period is over. And you'll have all this exact information on Friday when you do it with the Walters. Okay. And because I know some of you still haven't gotten your midterm back, just a quick thing on that too is whichever you do better on, because I know, and I don't want to get all bogged down in this now, I'll say it more on Monday, but because I know I've put you in a bad spot by not really having, many of you, by not having proper midterm information to use to go into the final, I'm telling you right now that whichever exam you do better on will count more in your average than the other one. I can't drop any exam because we only have 2, but I'll just repeat, that'll be repeated, but if you do better on the final, then it'll count more. If you do better if it turns out that you did better on the midterm, then that will count more for you as an individual. Okay. So, okay. Okay. So you hear me. Good. Fine. And finals. And thank you. And yeah, the final will be take home. It would be just like the other one, but shorter. Like you did the bulk of your work for the midterm. But yes, the final will be take home, open, universe, all that stuff. I'm rushing now because I kind of want to finish this homework to wrap up but yes. And Claudia's saying that things end on the 20th, the finals end on the 20th. Wait. So that's 2 weeks from today, right? That's 2 weeks from today. Right. So your final will be due back, like not that it'll be due back probably like the Sunday night or something of finals period, something like that. But you'll have like 4 or 5 nights to do it. It'll be handed out or posted right after you finish your last class or that night of next Monday. Sorry, I'm rushing. Okay, I'm glad I'm looking at the chat now. So again, this will be more clarified for Friday when you will see the practice final and all of that, and the Walters will help you, or whichever Professor Mr. Walters, I think, et cetera, et cetera. Okay, I'm just looking. Okay. So hopefully that's sort of clear. I apologize that that's okay. But now I'm looking at the physics chat. I mean, Claudia's. So each component of the sum of the work. Okay. Oh, yes, 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 yes. Oh, a great question, Claudia. That is what I was trying to say before, but not saying it well. Right, right, right. So like so I'm on Claudia's physics question now. And again, like thank you for your clarity on okay, I'm assuming we're clear on the other thing, but yes, what Claudia is saying, right. Net work means sum of all of the works, just like net force means sum of all the forces, and sum means add, but some terms might be negative. Yes, each individual work term, each individual work is itself, strictly speaking, a path integral. Strictly speaking, each one is an integral of a dot product, which means each one, strictly speaking, has to take into account angle, and each work term has to be the product of the matching parallel components. Yes, good question. Right. So good. Yes. Okay. So I'm going to keep going. Okay. 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 So we just did the network. So now E is kind of the key question to the whole thing. E is the key question. E is asking, well, E says, assume that at top of ramp, the initial speed is 2 meters per second. We want to know at bottom. Okay. At bottom, we want to know how fast it's going. Right now, I'm not saying that. I mean, this is sort of a plug-in, but this is the key concept here. We're going to use this work kinetic energy theorem, this idea that work transfers energy. But I want to, well, actually, let's just do it. Okay, okay. So we say net work done on an object equals change or transfer of kinetic energy, right? That's the theorem. I'm just writing in English first. Like, I do positive work on you, I give you kinetic energy. That's the whole idea here, right? So we've already, and to give you kinetic energy, excuse me, means to change your 1/2 mv squared from some initial value to some new value, right? If I do positive work on net work on you, your kinetic energy will go up. If I do negative work on you, your kinetic energy will go down. And by the way, Newton's third law is still true, and the whole thing still is an exchange, a transfer. So one of the reasons we keep taking into account negative work, is this a moment to say? I mean, just to be clear, if I exert a force on you, you're not necessarily exerting the exact opposite force on me. So if I do positive work on you, like in this case, Earth, in this case, planet Earth is doing positive work on the boulder, right? It's pulling it down and the boulder's going down. And so the planet Earth is giving energy to the boulder. Well, necessarily that means the boulder is doing negative work on planet Earth. If the boulder is getting energy, the Earth, that's coming from the Earth is losing energy. I mean, it's all a relationship, right? But okay. So the positive work that we're doing here, the positive net work that we're doing here, we just figured out was 7936. And that's going to yield the change in energy and just one subtlety here while I'm doing it, or it's not really, just please notice that I keep saying work is the transfer of energy, the change in energy. We're not saying that net work done equals 1/FMV squared. Like that is honestly, that's a common misconception. We are not saying that work done equals 1/FMV squared. We're saying it equals the change in 1/FMV squared. So, which is why they had to give us an initial value. So and I will, and I have a feeling, as I say, I'm going back and forth in screens, so I'm missing the chat at the moment. I will go back and look at it. And I'm definitely glad that at least one person did ask. Doing this, a question. Okay, I think this is the answer. If I didn't make a mistake or if there isn't something, I'm gonna look in the chat. Also, I'm gonna grab a. Okay, there's nothing in the chat. So I think that's the answer. That's at the bottom of the ramp. And if nothing else, I just hope it's clear why we had to be given that value at the beginning too. Like, yeah, I just hope that because it's a comparison, it's a transfer. Oh, sorry, bear with me one second. I'm gonna get a calculator. Okay. Okay, so that's that one. I'm gonna go to the next one, but please feel free to keep the chat question. I hope that's clear. Okay, so now we go up the ramp. Okay, so this is sort of what I was saying a second ago about negative versus positive work. Okay. Okay, so it's the same, yeah. Yeah. Okay, so number one is okay, so now this gets into the subtleties. I mean, this okay. I mean, all the same numbers, much of it's going to be much of the same computations, but the reason for this whole problem, it's not meant to be. I mean, the purpose of this problem is it's really trying to get at, honestly, what Claudia asked like 15 minutes ago. It's really trying to get at when there's more than one force doing work at the same time. It's forcing us to keep the different, each force does its own work. The sum of all of those works is the net work, right? So each force does its own work. You add up all the works together and you get the transfer of energy. I mean, it's much like F net equals ma. You look at each force individually first, then you add them all up and you get the acceleration. Okay, similarly here, but just like with F net equals ma and free body diagrams, one of the reasons you have to focus so hard on force components and all of that is really at the end of the day to make sure to keep the minus signs straight. Like the minus signs are kind of the challenging aspect of a lot of this, and the minus signs do matter. Some works are positive, others are negative. So that's what this is asking us to keep straight. All right, so A, what's the work? So this thing is going up, right? It's good. I mean, Sisyphus is successfully pushing this boulder up. But the question A is not about what Sisyphus is doing. Question A is what's the work done by gravity while this thing goes up, right? So the answer here, the work done by gravity is mgh, but it's going to be but it's negative mgh, right? Like whether you want to call it negative mg times h, or you want to call it mg times negative h, gravity's pulling down while this thing goes up. So gravity is, if you want to put it this way, is like failing in its mission, right? And put another way, if gravity were the if gravity were the only thing doing work right now, then the thing would be slowing down, right? But I don't know that it is slowing down because it's net work that yields transfer of energy. So I'm not asserting that this thing is slowing down, but if it were just up to gravity, it would be, because gravity is going in the against its motion, right? All right, I'm over talking for as usual. So, but the answer is it's going to be negative 85 times 10 times 11, right? And that's that number that I keep like not having. That number is 9350, right? So it's negative 9350 joules, right? That's the answer to question A of 2. Then B, calculate the work done by friction. Okay. On the boulder, as Sisyphus pushes it up all the way, right? Okay, we've already gotten that we've gotten that answer. That's definitely negative, and it's it's the force of friction. I'm using lowercase f to mean force of friction. It's a force of friction times the displacement, which we got before. It's 1414. Right? Again, stop me if you're not with me. So that's B. Then C, calculate the work done. Now so this now C is work done by the normal force. That's important. Well, it's important to understand. The normal force is a force. It is in the free body diagram, and there is displacement occurring here, right? But it's not a trick question. It just wants you to. But the point is, it would be, if you want to be technical about it, the work done is the normal force dotted with the displacement, right? And that means the normal force times the displacement times the cosine of the angle between them, between those two, between normal and displacement, and the angle between, not the angle of the plane. So you could use, I mean, you could call this, let's call this, I don't know if this will make you less confused or more, but I'll give it a different, call it cosine phi, like a different angle, not the angle that's given in the plane, but the angle between the normal force and the displacement. Well, that is 90 degrees, right? Like the normal force exerted by the plane is necessarily perpendicular to the surface of the plane. That's what normal means. So the cosine is 0. So the work done by, I don't care how big that normal force is, or how big the displacement is, the work done by the normal force is 0 joules. Yes, wait, I'm just going to look in the chat to make sure. That's important. That's not a trick question. I mean, it's not a trick question. We're trying to reinforce that you're always multiplying parallel components in order to calculate work, and therefore, when the components are perpendicular, you get nothing. And I'm going to say it one more time, then I'm going to look in the chat. The normal force, it doesn't mean the normal force isn't there. The normal force is in the free body diagram. The normal force is doing something, and we need to say we need to say at some point what it is doing. It is doing something super important, but it's not doing work. It's not transferring energy to the boulder. If you really want to know the fast answer, when we say a force is perpendicular to a displacement, in fact, I'm going to write this down. Oops, sorry. I just drew. gonna make this. Okay, this is. I want to remind you, and I will look in the chat in a second. We're emphasizing over and over in this whole topic, in this whole homework sheet, that the component of force that is parallel to displacement does work, right? Therefore, transfers energy, therefore affects, or let's say changes speed. The component that does work affects the speed of an object. The component that's parallel of an object, the component that's parallel to the displacement of an object affects its speed. What I want to say right now is, what about the other component? What about the component that's perpendicular, such as the normal force? Like, what is the normal force doing? We're going to write down the contrast is this, and then I'm going to go on, but we need to know this, especially for physics 204. The component of force perpendicular to displacement, perpendicular, right? The other, like normal force, e.g. normal force here, changes not speed. It doesn't change speed, right? It does no work. It changes direction. Or you could say it affects direction, if you like. Like, remember, F equals ma. All forces, or ultimately net forces, accelerate objects. To accelerate is to change velocity. Remember, velocity consists of two pieces of information, two measurements, two properties, speed and direction. In the end of the day, your speed is changed by any component of force that is parallel to the direction you're moving, and your direction is changed by any component of force that's perpendicular to the direction you're moving. Velocity consists of speed and direction. Forces change velocity. You see what I'm saying? I'm going to go back to the homework now, but that's an important, for the very last class, and for 204, that's an important distinction. So the other force component isn't wasted, but it turns you. Forces change velocity. Forces change velocity because forces accelerate, right? Okay, so back. So anyway, so the answer to, I'm going to look in the chat. I'm sorry. Wait, there might, there is something in the chat. That's so good. There should be. Good question. Oh, yeah, but oh, wait, oh, yeah. Okay, awesome. All right, yes, great question on Maria's part, and great collegial affirmation or multiplayer co-op on the part of Claudia. You should both really, especially at this point of the year, both of you should submit for points for that. That makes me so happy, especially because I can't see anything. But yes. Okay, so Maria's question is good. Yes. Normal force, as long as you're, be careful what you're saying or what you're thinking, yes, normal force, well, the normal force to a surface is always perpendicular to that surface, yes. So yes, the angle between the normal force and the surface itself will always be 90 degrees. You can always assume that, yes. So as long as I'm being careful and you're being careful, therefore, you can always assume that that's 90 degrees, and you can always assume, therefore, that the normal force will do no work on any object that is sliding along that surface. That is, yes. I mean, as long as you and I and Claudia and everybody are saying the same thing, then yeah, you can take that to the bank. What am I trying to guard you against? What am I trying to guard you against? Right. The normal for any object that's going along a surface, you can believe that the normal force is doing no work on that object that's going along the surface. And so, to put it in English, what I'm saying is, well, what is the normal force doing? Like, why is the normal force even relevant? Well, two reasons. One is the normal force is contributing to friction,
which is ultimately doing work. So I want to, like, that doesn't contradict what you're saying, but I hope that's clear. But also the thing about the normal force is, if you really step back and look, what the normal force is really doing is affecting direction. Like if the normal force weren't there, if the ramp weren't there, this boulder would just fall, would either fall straight down or Sisyphus would push it straight up, right? But the angle is affecting, so it is affecting velocity, just not in the speed aspect of velocity. It's affecting the direction. It's because of the ramp that the thing isn't going in a vertical line. But yes, okay, good question to Maria and to Claudia. You can always assume in fact, I will say this, if you want to write down a truism, the normal force, I can't think of any exception to this rule that I'm saying. The normal force never does any work on a sliding object. Like that is true. The normal force does not do, the normal force from a slide does not ever do any work on the sliding object. Like, yes. Okay, okay. So I'm gonna keep going, but good question. Let's keep, oh, there's something else in the chat. Yay. Oh, gotcha. Okay, cool. Oh, so she just got like they just got like 3 point, right? Like submit for points for participating, and then for multiplayer co-op, and then for closing the loop. Okay, there's still time. And any old homeworks or any things like that, by the way, I'll take through Monday, through midnight of Monday, the last day of classes. Sidebar, but okay. Not the one thing I won't take is like old game turns. I'm saying this to everybody. I'm not just talking to Maria. Like if you have like a daily game, like turn number 18 from a week ago for 5 points of that, those, please do not, like, it's not worth it or relevant at this point to take those. But things like multiplayer co-op or showing video or whatever, or old, I will take it. Okay, you get my point. All right, I'm going on. What time is it? Okay. So that was C. Okay, right. So now we're doing D. D says it pushes with a constant force of 700 newtons. Calculate that worked. Oh, okay. Okay, so now it's just saying, so Sisyphus, it's just telling us that Sisyphus pushes with 700 newtons, and he's pushes up the ramp with 700 newtons, right? And that in itself couldn't tell us whether that's positive or negative, but we know that, but we know that he's pushing up. We look at the picture and we know the thing is going up, so that work will be positive. The work, and he's pushing, you look at the picture, he is pushing along the ramp. He's not doing anything, he's not making any he's not making any angle with the displacement of this. And again, right, I mean, back to Maria's question and Claudia's affirmation, like work, it's always about, and I think this is the thing that does confuse people, work itself as a concept, as an equation, is always concerned with the angle between the force and the actual displacement, right? That's the angle that we always care about when we're calculating work. That may or may not be the same thing as, or related anyway, to any other angle that we're given in the problem. I'm just going to say this one more time and move on, but like, don't be fooled. Like, we're never trying to trick you in physics. It's just that there are things that are tricky, right? Like, we give this angle of 33 degrees, we present it in the problem because it's is totally relevant to the problem. Like the angle between the slide and the horizontal line of Earth, that is relevant, but that's not the angle that we mean every time we say work looks at the angle between force and displacement, right? That's just an angle in the problem. It might be related to the angle we're looking for whenever we compute work. It often is, but we always have to bear that in mind. Like I think I just hit it. Like, we give you an angle in a problem, but the work equation refers to an angle already. Do not assume that those are the same angles. From now on, maybe I should use 2 different notations for them or something. But okay, like that's anyway. Okay. But so the work done by Sisyphus, that is fully along the plane. I don't need to use the angle for this at all. The angle between the force that Sisyphus is doing with the plane itself, that angle is, just to be clear, is 0 degrees. Right? I mean, just just like with friction it is. All right, and so the force exerted by Sisyphus is 700 newtons, and the plane is the number that I keep not calculating, 11 over sine of 33 degrees, right? So the whole thing, which I really should get once and for all. Okay, right, and it's like 20.2, yeah. And I probably really should have been in scientific notation this whole time. But I wasn't, but I am now. And this is, okay, so I think the work done by Sisyphus is, excuse me, is positive 1.41 times 10 to the fourth joules of work. Okay, so then I'll look in the chat again in a second. So then it wants the net work done by the boulder as Sisyphus pushes it all the way up the ramp, right? So this is now, okay, okay. The net work done by the boulder, excuse me, the net work done on the boulder. So this is like a little bit complicated. So this is E. We want the net work on boulder. That's the question, right? And this again is back to Claudia's original thing, like the net work done on boulder is the sum of all of the forces doing work on the boulder. Now, it's not the sum of all the force. Well, it's the sum of all the forces doing work. Now, I'm not going to worry about the normal force because it's doing zero work. But every other force that's ever come up every force that has any component along the plane counts for this calculation. So it seems to me the net work done on the boulder would be gravity, excuse me, would be the work done by Sisyphus up, right, positive, minus the work done by friction, which is because, okay, sorry. The work done on the boulder is the work done by Sisyphus plus the work done by friction plus the work done by gravity. Only the work done by friction and the work done by gravity are both negative amounts of work, right? But I'm accounting for everything that has any component that lies along the plane. I'm just using S to mean Sisyphus and F to mean friction and G to mean gravity, right? So I think what we're going to get is something like this, and the work done by friction oh. So I really should not be rounding anymore. I should be more careful, shouldn't I? Jeepers. All right, hold on a second. Maybe I should be more exact with this thing right here. All right. I'm being slightly more exact. With the work done by friction. Wait, something's wrong. Sorry, I'm really losing I think I see what I did. I'm missing a zero somewhere, aren't I? I'm off by a power of 10. Hold on, I just want to see one. Right, because the friction, yeah. I'm off by power, so it's not, okay. So this was supposed to be, oh, no, I'm only off in my mind. Lordy, okay. In other words, I'm going to look in the chat in a second because I'm sure I'm causing all kinds of stuff, but I think I see what's happening. All right, I think it's something like this. I'm gonna look in the chat in a second. I think it's something like that. Okay. Right. Okay. Wait. Okay. So looking at so first of all, I think this is the answer. I freaked myself out for a minute because I thought that the work done by Sisyphus was given as the same number as the work done by friction. I thought they were both 70, which would really make very little sense. But the work done by Sisyphus was 7, or the force of Sisyphus was 700 and the force of friction was 70. So there was no problem. I just freaked myself out. I think this is basically the answer. You should check your numbers. If your numbers are essentially the same as mine, good. But if you got something wildly different or a completely different number of zeros, you should say something in the chat. But then also, so Maria's asking, yeah, ideally, yes. Scientific notation is good for a reason. We're not in the middle of lab, and we're not mixing chemicals or something. So it's not that I'm like that hyper about scientific notation. And if sometimes you're doing like 3 significant digits and sometimes 2 or something, that's not my big concern in this. But once the numbers are getting a little crazy and unwieldy, once they're in the thousands or 10,000s, it really does become more convenient and organized to look at them in scientific notation. So the answer to Maria's question is yes, ideally. Right. Okay, cool. Right. Okay. And honestly, and the reason I just got for what it's worth to anybody, I introduced scientific notation too late for my own good in this problem. Honestly, the scientific notation makes things a lot more clear to me at this point in my life. It's not that the scientific notation started making things confusing. It's that I wasn't using it at first and then introduced it. So it became hard for me to compare my numbers, and that's on me. But anyway, all right. So now someone else asked in the chat, I'm not sure if this is in response to what I just said but yes, someone's asking privately in the chat, am I still taking old homework? So the answer is yes, I will, or updates or revisions or whatever. I will through Monday. Don't overwhelm me. Be selective, basically, is what comes down to. If you've never done any homework in this class to this point, it's not to your benefit or to mine for you suddenly to give me a stack of 10 homeworks fresh, off the presses. On a number of levels, that's a bad idea. And it just doesn't make you look, it doesn't find favor in the universe's eyes to do that. But certainly, if you have an old one here or there, or a couple of them or something, yes, you could still turn those in by Monday night. Or if you want to turn in revisions on something. And also, I'll just say, as long as we're talking about this now, this same sort of grading policy with the homeworks. The general attitude here is I want you to do well. I'm not being sarcastic. We're looking for people to get good grades that they earned, right? And the benefit of the doubt goes to you. I hope you understand that at this point. And I think I gave a lot of speeches about that right at the beginning of the semester. But what that means in terms of homework is if you ever got a homework back from me where you didn't get a perfect score, and if you got feedback, then you can fix things and get a better score, and you still can do that here or there before Monday. But if you ever got a non-perfect score and you didn't, I would say 3 is right on the. If you have 3 things that you want to turn in for improvement, that would be right on the edge. I mean, go for it. Maybe if I'm overwhelmed, maybe I won't be able to deal with all of them, but there's no risk. I think more than 3 would be a little silly for anybody. I'm just answering what's in the chat here, but 3 is right on the threshold, sure, and it won't hurt you to do that. But similarly, if there's ever, and I want to move on in a second, but if there's ever a situation where one second, I'm sorry, things are happening. 3 things are happening at once. Okay. What was I just gonna say? If you ever got a homework back, like even a while ago, that was a low score, but you don't see any feedback on it. If you don't see feedback and it's like a lower score, if it's obvious what to do, like you didn't put all the pages together or the page or it's missing pages or something, if it's like obvious that you're missing a lot and that's why you got a low score, you can still turn in a revision on that or whatever, and that's fine. But if you did a homework and you did it thoroughly and all that, and you got a score that's not a perfect score, but you didn't get feedback, don't worry about that now, because that means the ball's in my court and I just have to raise the score. I mean, to be blunt, okay, and I will. I hope that's clear. So don't worry about homeworks where you're like right on the edge or you were close to a perfect score, but you didn't get a perfect score, but you don't even know why. Don't worry about it now, because I know that that's the case too, and you will get the benefit of that situation. Okay, I hope that's clear. But yeah, okay, I'm gonna move on. Wait, and I'm looking in the chat. I did not get the answer. Oh, great. Very honest thing in the chat also. So someone's and all these things, I hope you've been submitting for these participation points. But yeah. Someone's just saying in the chat that they didn't get a correct answer here because of a misunderstanding about the role of the normal force, but now they understand it makes more sense. So thank you. So thank you for saying that. Yeah, like, and this is just like if you included all of the forces in your network, including like normal force somehow, and so then yes, you would get the wrong number here. And and if this were an exam or something, I'm not going to punish you a million times for the same error. So I mean, if you did all this correctly, but you already got the normal force, like fine. But yes, one big takeaway here with 20 minutes left of class, one big takeaway is, I'm going to say it again because it's like one of the last big points we're ever going to make in this semester is the force component that's lined up with your displacement changes your speed. The force component that's against your displacement, that's perpendicular to your displacement, changes your direction. It turns you. Like how? Okay, like how? So we do have to track these things like the normal force. They're doing something, but what they're doing is changing your direction. They're ultimately sending you in if nothing else would happen in a problem, if something kept knocking you to the side while you were going forward, if something kept knocking you to the side, it would start curving you. It would send you into a circle. And one of the last things we ever have to say in this semester is like, what happens when things are moving in the arc of a circle? How do they get there in the first place? And the answer is something exerts a force on them perpendicular to their motion. Okay, so anyway, but thank you for the person in the chat who acknowledged that. Okay, so I'm going on to part 4 of F. All right, so the network was that. All right, so then F, I'm sure you can see where this is going. So then F says if the boulder started from rest, calculate the final speed when it reaches the top of the ramp. So it's the same thing as before, right? Network equals change in kinetic energy or transfer of kinetic energy. The network here was 3.38 times 10 to the third. And the change in kinetic energy is 1F mv squared minus 1F mv naught squared. Now, in this case, the thing started off with 0 speed in this case, right? So here's where it looks like I'm saying that the work done equals the 1F mv squared. Like one of the two 1F mv squareds cancel out. But please note, like that's just because one happened to cancel out because one of the speeds here happens to be 0. But we are saying for all time that what work you do is the work you do in joules is what changes the kinetic energy by that amount of joules. It's not that work is energy, it's that work transfers energy, right? Okay. Oh, just changed my color, but didn't mean to do that, but I did. Correct me if my math is wrong here too. Yeah, I am being kind of inconsistent about that scientific notation. It's one of those days, apparently. All right, so I think this is the answer. I think the answer is like 8.92 meters per second. I'm looking at the chat just to make sure. Okay, the chat looks okay. Blah blah blah. So that's F. There's a lot going on here. Okay, well, okay. Oh, well, those are all hints. Okay. I'm just gonna keep going. So now we do the piano mover. Oh yeah, so this is like the sled thing right now. This is just making sure again. So I cannot draw a piano. So this is a piano. Okay. And this is the push. And it's 15 degrees below the horizontal. Right. And the piano is 200 kilograms. Okay. Okay, well, this is all right. This hopefully is not. So question A is if X, and again, let me remind you, don't forget for physics for your life, for physics 204, work is the integral of force with respect to displacement. It's the path integral of F dot dx. It is an integral, but we have not used that integral once in this homework assignment, and we won't, because in all the questions in this homework assignment, the force is constant. I'm just reminding you, like, we want to set you up for physics 204 with this understanding of integrals and all of that, and with this recognition that forces can change from place to place, and then the calculus is necessary. Here, the force is whatever is happening in all these problems, the force is remaining steady from place to place. So every one of these problems, I've taken the F out of the integral, so to speak, and I'm instead of doing integral of F dx, I'm doing F times integral of dx. And integral of dx is always X. I don't know if that just okay, that's just an acknowledgement. And the same thing here in this problem. Like, again, no matter how complicated it does or does not look, the force is staying the same. So I'm not doing calculus here. So if X equals 20, that's why I keep writing X instead of DX. Okay. How much work does a piano? Okay. And the piano, and we're assuming the piano, like the piano is moving in the direction. Those are like wind. The piano is moving in the direction that the thing is pushing. So the right. And again, this is sort of just practice. Again, you could think of this as 40 times 20 times. You could think of it as 40 times 20 times the cosine of the angle between them, or you could think of it as 40 times the cosine times 20, same point. Either way, that's sort of what we're trying to get across. So it's 8,000 times the cosine of 15. Oh yeah, and so then B, so that's the answer to that. The piano mover does like 7.73 times 10 to the third joules. Then B asks, how much work does gravity do? Work done by gravity. And this goes back to someone in the private chat before, well, Anne Maria. how much work does gravity do on the piano during the course of the 20-meter trip? Well, gravity is a force. It is in the free body diagram, and there is displacement here. But the displacement is purely horizontal, and gravity is purely vertical. So the work done by gravity equals 0 joules. Like, strictly speaking, it's mg dotted with x. It's mgx times cosine of the a. See, again, this is what I was saying before. I'm going to move on. I always say that. I'm always lying. But I'm saying I know what I'm going to do in the future. In the future, I'm just going to call this angle phi instead of theta. Like the definition of work is force magnitude times displacement magnitude times cosine of the angle between the force and the displacement, right? If we're looking at the force of gravity and the displacement of this piano, the angle between them, between those two vectors, is 0. Excuse me. The angle between them is 90 degrees. And so the cosine is 0, right? And even though the angle given in the problem is 15 degrees, that has nothing to do with what we're being asked right now. That has to do with what the worker did. I don't know how to explain it. I think I'm over-explaining it for some of you and under-explaining it for the others of you, but the work done by gravity here is 0 because the object is moving purely horizontally. So gravity is not transferring any energy to the, that's a way to think of it too. Like, gravity's there, but what is gravity slowing down this thing or speeding it up? Neither. Gravity has nothing to do with why this thing has speed. Okay, I'm going to move on. Finally, all right, this now, it gives you all these hints and stuff, and it all looks like a very long problem. I think for the sake of like semester closure and clarity and all that, we still have one more class next Monday, which I know is weird, but I'm relying on it. We have one more class next Monday. You have review and everything this Friday with Walters. So on this one, I think just so we can feel, I'm going to stop talking. I mean, we've got 11 minutes. I think what I'm going to try to do is just like write down the answers to this. I'm going to try to keep my mouth shut while I do that. And then you look at the answers and, see whatever question, when I'm done writing down the answers, you ask whatever questions you want. But my goal will be to shut up and just give you the answers to this so we can see whether we're, good or not. Okay. I think that will work for many of you. It's probably what many of you have wanted all along. All right, so yeah, so I'm just going to quietly do this out right now. But you should stop. I'm going to just keep going. We've got 9 minutes. But if I write something that you're pretty sure is wrong, or you're really confused, like, wait, I thought that was clear and I don't know, then obviously stop me or at least put it in the chat. But okay. There is something in the chat. Wait, before I turn the pages. Oh, okay. Sorry. Okay, I'm looking in the chat. The answer to Maria's question is yes. And you know what? Honestly, you can thank Oh, you don't know. You could thank one of the lab instructors for that. They're forcing me to not deal with it until next. So yes, Maria. Good question. But you definitely the next semester starts off right away with that issue, just so you know. Okay, but yes. Okay. Wait. Okay. And thank you, direct chat person. Okay, I'm gonna go on. I was stalling slightly so I could turn the page before you. I mean, so you can get the page before I turn it, but okay. Yes, good stuff in the chat. Okay. T. Okay. Yeah. Yeah, I'm gonna turn the page. Let me know if you. I mean, yeah. Hmm. Wait, I've done something wrong, haven't I? God darn it. Hold on 1 second. Oh, did I put the mask wrong in somewhere? One second, sorry. Hmm. Oh yeah, no, okay. Sorry. We're looking at the time. Okay, we've got 4 minutes. About the work. Same as
0. Wait, it's not, yeah. Okay, um, okay. So it's 129. I think I just got all, yeah. Um, I'm looking at the chat. Those are the answers. I think this was actually the right thing to do. I will summarize what the answers mean and why or whatever at the beginning of our very last class on Monday. Then I am going to teach one last thing Monday, or I'm going to bring the concepts together with one last concept on Monday. And I'll reconfirm the details of the final exam and all that, but you will be practicing and wrapping things up together for your final exam and everything in Friday in lab. So, okay, so I hope at least these answers. So if any of these answers confuse you, should come in on Monday with anything you don't understand about whatever I just wrote down. And other than that, have a very, very nice 2 days, a nice lab, and a nice beginning of the holiday if it is a holiday for you. Okay. Hey, have a nice day. Yes, have a great day. Have a good one.